In this video, we're going to look at example 8 in the textbook. Before we talk about this example, let's recall the previous sections, the previous homework. What we did was to use sample mean to approximate the population mean. We know population mean is the mean of the whole entire population, but sample mean is just the mean of a sample. So these two could be different, and it's practical to find the sample mean, but it's not easy to find the population mean. So most of the time in real life, we just use the sample mean to approximate the population mean. But since we know there's a most likely a difference between population mean and the sample mean, mu, that sometimes we give a confidence interval for population mean. Suppose we found out the sample mean, and we can use the formula to find a range for population and mean. So for example, if we find out the sample mean is 20 and the population mean might be between, say, 15 and 25, or maybe it might be between 16 and say 24, something like that. So population mean mu falls in a range somewhere near the sample mean. But in this section, we do something totally different. We don't give a range for population mean. We have first we have a claim. We call it a hypothesis here. For example, in example 8, we have a claim. The seller of the teller machine, and they claim that their machine average transaction time is less than 270 seconds right here. And we know that if we want to support or reject this claim, we need to do our own research. So we recorded 38 transaction times of the teller machine, and we found we can use the formula we did before to add all the transaction times divided by 38. So that's the sample average. But we found out the sample average time is, let's see, some certain number. For example, what if we got 269? And so if we get 269, should we support the seller's claim that the population mean is less than 270? Not necessary, because 269 is only the sample mean, it's not the population mean. So the sample mean is 269 does not guarantee the population mean is going to be less than 270. Okay, but we want to know. So maybe we found out this sample mean is 240. Is that small enough to support their claim, the population mean? Because 269 is sort of too big, because it's a sample, and we know from our experience before, the population mean could fall in the near area, a close area of 269. So it might be 275, it might be 264 or something like that. So 269 is not too good. It's not so good for supporting this claim. So how small this sample mean has to be for us to support their claim? So this is the question here. And in this example, they give the sample mean is 261 right here. So I said 269 is too close to 70, so it might not be good to support their claim that mu is less than 270. But is 261 small enough? Okay, so this is the question we're going to answer. And so before we talk about that, I'm going to explain using this picture right here. Okay, so this is the question. Then we call it alternative hypothesis. So this is a teller's claim. Mu is less than 270 seconds. So that is saying the average transaction time for all the machines they have, all the transactions, for all the transactions they have is less than 270 seconds. But we are trying to test. We're going to make a opposite assumption. So what if mu is greater than or equal to 270? So this is called a null hypothesis. And you can see I didn't write down mu is greater than or equal to 270. I put it mu is equal to 270 because if mu is equal to 270, mu cannot be less than 270. So mu equals 270 can be considered as the opposite of mu less than 270. So these two hypotheses, they are opposite of each other. And if you found out that you're going to support a mu less than 270, that means you're going to reject mu equal to 70. If you're going to support mu equal to 270, then you're going to reject mu less than 270. So that's you only support one of them, reject the other one. Okay, so here we want we're going to do a research to find out average transaction time, which is denoted by x bar sample mean. And I want to know how small the sample mean x bar has to be in order to support alternative hypothesis, which means to reject null hypothesis. And of course, you want the chance of making a mistake, either rejecting or supporting, to be very, very low, So for example, 5%. You want the chance of making a mistake of your conclusion is very low. So that's why we pick 0.05 here. That means 5% chance. 5% chance of what? Again, go back to what we talked about before. We want to know okay, their claim, the alternative claim is the alternative hypothesis is the vendor's claim. They're saying the transaction time is less than 270, and we cannot find a mu. We can only find x bar. So we want to know how small x bar has to be in order to support vendor claim. In other words, to reject null hypothesis. So the chance we want the chance of supporting 270 to be the chance of rejecting the null hypothesis to be low. And so when x bar is less than which number? So you can see from the picture they're showing that x bar is less than 263.6. I will explain how they got this number in a second, 263.6. To make it easier to say, I'm just going to say 264. So how did they find 264 right here? So they're saying when x bar is less than or equal to 264 seconds, and it's good enough to support the hypothesis claim, which means you can reject null hypothesis. So that means the chance of making a mistake of rejecting the null hypothesis is only 5%. So if you only have 5% of chance of making a mistake, and then that means that is good enough. So the question now is, how do we find out 264 here? And we know the area under the curve means the probability. So we want the probability to be 0.05. And we did this exercise a lot, and also in the second exam. And you can go into the table and found corresponding z-value. So for a second, let's forget about x bar and 264. Look at this, the bottom one, which is z, corresponds to z. So in the middle, it's the population. It's population mean 0. It's the standard normal distribution, and so the population mean is always 0. And this is the z value. So for what kind of z value, we will have the area under the curve equal to 0.05, or you can say probability is 5%. And so we go into the table, we found 0.05, and then we found the corresponding z-value. We know it's negative 1.645. Okay, so it's this z-value right here. And then, but how do we find x bar? Because we know we can convert x bar to z. And so z, in other words, we can convert z back to x bar. A different way to understand this is because what does this z-value mean? This z-value, so this point right here, this region, this black line here means it's a region. That means z is less than or equal to negative 1.645. That means it's on the left side of negative 1.645. But if we just look at the point, this point right here, negative 1.645, this z-value, it means how many standard deviation you're gonna have. So starting from the center, if we take a 1.645 standard deviation, you're going to get this point right here. Okay, so if we go back to the distribution for x bar, we know x bar by central limit theory. X bar is approximately the normal distribution. So x bar, the curve looks like a bell-shaped curve, and so we know that we want to find the corresponding x bar point. This is the z point, this is x bar. So the difference between z and x bar is z is the normal standard variable, but x bar is just a normal random variable. It's not necessarily standard. And so where's this point? It's 1.645 standard deviation from 270. So we take 270. So we can look at this calculation here. Oops, right here. Okay, right here. That take 270, subtract 1.645 standard deviation. So from here to here. So from 270 to this point, it's 1.645 standard deviation. So I take 1.645 times 24 is the standard deviation divided by square root of 38, because this is for sample mean, and we use the formula, and then we get 263.6. So we find this point here. So this point right here is very important. It's the cutoff point. So we say that, you know, if your sample mean is less than 263.6, and then we will substantiate alternative hypothesis and reject null hypothesis. Okay, and if we go back to our example, in the other words, if z value here is less than or equal to negative, whatever your z value is falling into this category, and then you can support alternative hypothesis. So all the explanation before, I was trying to explain why if the value falls into this category right here, this black region right here, we will support alternative and reject null. And so one more time to explain this, that because the chance of rejecting the null hypothesis, the chance of making a mistake by rejecting the null hypothesis is only 5%, which equivalents to saying the chance of making a mistake of supporting mu less than 270 is only 5%. So the chance of making a mistake is very low, so you can say you're going to support mu less than 270. Okay, so if we go back to example 8 here, you can see it's 261, which is less than the cutoff point, 263.6, so you can definitely support the claim. But we didn't do that way. Instead of doing that way,